Hello everyone. I'd like to talking about the rigorous solution enclosures of differential equations between sub and super solutions constructed by neural networks. And this is the joint work with Kohei Yatabe, also belonging to Waseda University. This is the information about me. I'm Kazuaki Tanaka from Waseda University. The birthplace is Sasebo, Nagasaki, Japan. And I have been belonging to Waseda University for a long time. This is the overview of my talk. In the first section, I'd like to introduce our enclosure arguments based on sub and super solutions for the initial problem of ODE. And then in the second section, I'd like to show that such arguments can be extended to our elliptic and parabolic problems with some examples. And then explain a method for computing and approximate solutions to this problem with our neural network. So this is the main part of this talk. And then show that the sub and super solutions method can be well fit to its verification. This is the classical argument of sub and super solutions, and which is not already known result. And this classical argument can be extended to the various cases. However, these can be proven by almost the same method as this classical argument. Suppose that, yes, this classical argument is suppose that there exists a pair of functions which will be called sub and super solutions that satisfy these inequalities. These inequalities can be given by replacing these equality to these inequality. And this is the critical assumption. If this order is satisfied, and f is continuous over this vision, then our exact solution U of the target problem exists and satisfies these inequality. So the exact solution exists between sub and super solutions. Yes, and this can be proven by these steps. First, define our function t as this. T is called a truncated function because t returns always u if u is between sub and super solutions. However, if u exceeds our super solution, then tu returns super solution. And moreover, when u less than our sub solution, then tu returns sub solution always. So t is called truncated function, truncating function. And moreover, we prove the existence of a solution u by replacing ftu to fttu, yeah, with replacing this part. And finally, prove that the solution satisfies these inequalities. As a result, we can prove the tu always returns u. Therefore, we can ignore the first replace this replacement. Yeah. As a result, we can prove the existence of solution u between our sub and super solutions. And this type of this proof steps can be used for the more general version of this type of arguments. Yes, for example, this is the extension to be effective in numerical analysis. The different points are yes, a little bit the assumption is a little bit be extended from the classical version because in the classical version we have to assume yes, sub and super solution should be smooth, C1. Yeah. However, in numerical analysis, we often want our sub and super solutions to be constructed by piecewise linear or piecewise smooth function. Yeah. So this can I extended the classical theorem to this. Maybe this type of argument has been already known, but I haven't seen yet exactly the same argument as this theorem too. So I proved that. And moreover, global interim solutions, the existence of global interim solutions can be proved by these theorem. And I also haven't seen exactly the same solution as theorems B. So I proved that, but not so difficult. Okay, this was the section 1. Next, I'd like to show that such an argument can be extended. First, such argument can be extended to elliptic PDEs. We now consider this a general elliptic problem. And yes, the sub-solution can be defined like this, just replacing these equalities to the inequalities. Yes, and the super solution can be defined in the same manner. For such sub and super solutions, we can get the existence theorem, existence argument based on sub and super solutions. Yes, supports these sub and super solutions satisfy this order. This is critical assumption. And if satisfies this closed condition, and then we can get the existence result between sub and super solutions. Yes, and please note that yes, this argument can be applied to the weak solution, weak sub-solution, and the weak exact solution. However, in more classic argument, when we consider the strong solution, a strong solution version were already given as monotonicity method. For example, in this book, which is very famous in our research area. Yes, and the next parabolic, we can extend this argument to even parabolic PDEs, and weak solution or weak sub-solution can be defined in the same manner, and almost the same argument can be given. Yes, even for parabolic PDEs. Okay, and I already applied to such argument to the Arlen-Kern equations, which are a stationary problem of Arlen-Kern equation, which is our elliptic problem. And I used here, I used Fourier extension, and I constructed approximations the candidates of a sub and super solutions by solving this. These delta perturbation is important to get our sub and super solutions. Okay, and this is the verification, my old verification result in 2016. When delta is equal to 10, we have this sub-solution and a super solution, and we have to check these inequalities that is if whether our sub-solution satisfies the the candidate of subsolution, because this equation was solved numerically. Yes, so we have to check this defect should be non-negative. Yes, and this verification was done by interval arithmetic, and we proved the non-negativity of this defect, and also for the super solution, non-positivity of this defect bound. So these candidates of sub and super solutions are confirmed to satisfy the definitions of sub and super solutions. And finally, the critical assumption is this order. This difference between sub and super solutions should be positive. Yes, and we proved also. So as a result, because we proved these three inequalities, we can get the existence of we can prove the existence of exact solution, and with this error bound. Yeah. And these error bounds can be reduced as delta, the perturbation reduced. And in the recent paper, we proved the global interim solutions using sub and super solutions method here. And you can see this paper in the channel, in my channel of Slack. Okay, this was that's all of section 2. And finally, I'd like to go to section 3 to explain a method for computing an approximate solution of the target equation with a neural network. Yeah, and at the same time, show that these sub and super solution method are well fit to verification. This is the conceptual graph of neural network. I call artificial neural network ANL. Yes, sorry. These are some we see some Japanese, but please allow me. Okay, here the function n neuron is given by this form, and here this W is called weight matrix, and B is a vector called bias. And we here, phi is a nonlinear function, and usually set to, for example, LU function or sigmoid function or arctangent function. However, we used a periodic activation function. This is recently studied function 2020. But this is very simple function because this is just a sine function. Yeah, and and the set of functions that can be expressed by A and N depends on the choice of phi and the number of layers or new layers and the neurons. And in this conceptual graph, this ANN has only 3 layers. However, more deep neural networks can be used. Okay, next, I'd like to explain how do we get the approximate solution by a neural network. Actually, we have to solve some optimization problem, and the solving the optimization problem is called learning. And to calculate approximate solution you heard from ANN, we use this cost function for optimization. And here, S is the set of sample points chosen from this region. And yes, again, solving being the problem, this optimization find you heard from ANN minimizing L1 via some gradient descent method is called learning. And we used Adam which is an optimization algorithm for A and N in our examples. And moreover, this slide is most important for explaining our method. The key is how to construct our sub and super solutions from A and N, satisfying this order. To this end, we use the cost function. We constructed the cost function that satisfies this. And here we see that there are 3 parts inside H. Here H is a convex function for positive region, and the first part is related with sub-solution, and the second part is super solution, and the last part is for satisfying this inequality. Yes, and moreover, H should locally minimize at t equal to epsilon for small epsilon, and this epsilon stands for the Alweb error. We have to set explicitly, and the parameters inside V and W are which should be chosen from A and N. Yes. So inside these, we have some matrices and the vectors are called weights or bias. Yes, and they are chosen to induce T to the positive direction. Yeah, and the interval arithmetics were used to confirm that the sub and super solutions satisfy our desired inequalities, the definitions of sub and super solutions method and the disorder. Yeah. And these are examples of H, and I like to show you in the real-time session the graph of H. Yes, this is the verification example 1. This is very simple logistic equation, and we can get the exact. We can know the exact solution, but for the first benchmark test, I verified, I enclosed the exact solution between the sub and super solution constructed by A and N. Yeah, and this is super solution and sub solution, and we can prove the order of sub and super solution, and so we proved the existence of exact solution between them. And the next example of this, and yes, this is a generalization of logistics equation like this. So we can't know easily the exact what is the exact solution, but the sub and super solution inside between sub and super solution, we can know the existence of exact solution. Yes, by the way, in the first example, we proved even the global the existence in global in-time sense. Okay, this was my talk. Yes. I have some future works I would like to try. The first thing is reducing the calculation cost, because I'd like to apply our method to more high-dimensional cases, and the key point is to prove the positivity of functions constructed by A and N. For example, this difference. For example, we want to prove the positivity of this difference. Yes, and then I like to apply our method to more multi-dimensional cases. For example, with our three-dimensional with time dimension, so four-dimensional cases. Yeah, and then now are trying now. And then moreover, this is also related to this reducing the calculation cost, but I'd like to use both GPUs and CPUs. In the previous, in this example, in example 1 and 2, I used only CPUs. However, many packages of a learning toolbox can be applied to our GPUs. So in approximate computing, I'd like to use GPUs, and then in the verification process, I'd like to use CPUs with interval arithmetic. Then we can reduce more the calculation cost. And the last one is I have to, this is our first example. So I have to evaluate the performance of this type of method. For example, tolerance limits, epsilon, or speed of convergence. Yes, and so on. Okay, that's all of my talk. However, I have a question to you. I'd like to ask to you, what do you use when you explain your keywords or your research vision? At least I know these phrases, verified numerical computation, which is used often in Japan, and a numerical verification method also mainly in Japan, but sometimes outside. Yeah, and the computer-assisted numerical proofs and computer-assisted existence proofs, or computer-assisted analysis, reliable computing inside of the recap name, rigorous numerics, validated numerics, and this is already to be interesting. Self-validating numerical methods or self-validated numerical methods, which is true, maybe both true, because our method validate, our computing method validates ourselves. So think that both are true. However, I can see both phrases. And some of them can be combined. For example, computer-assisted proof by verified numerical computations, something like that. And anyway, if you know other words, let me know via Slack or in the real-time session, because knowing such words is useful, helpful to find your papers, your new papers, or related papers, or teaching our students. Yes, so please let me know and discuss them in the real-time session. Thank you very much.